Swayam Prabha. Digital India. Educated India.
Welcome to the lecture 2 of course on time series modeling and forecasting. In the present lecture, actually we are not going to discuss any topic related to time series, but we are going to discuss some results of matrix algebra, regression analysis, and we will also discuss the method of least squares, because all these things you will require for the future lectures. At so many places we are going to use the matrix notations. So, I am going to give you the main results which we will require for the future lectures. Though I am not going to give you the detailed derivations. For detailed derivations, you may consult any good matrix algebra book, and then I will also discuss the simple linear regression model and multiple linear regression model and the method of least squares, and some other aspects of the multiple linear regression model. So, again you will require all these things during the course. So, first in brief I will discuss some results of the matrix algebra. So, what is a matrix? It's simply a rectangular array of numbers. Say for example, this is a 2 by 4 matrix, its elements are real numbers. The matrix has 2 rows and 4 columns. So, that is why it is called 2 by 4 matrix. Or suppose capital A is a matrix with elements aij's, means a11, a12, so on a1n and so on, am1, am2, amn. Then A is an m cross n matrix, it has m rows and n columns. Sometimes we also denote it by within double bracket aij. This aij denotes the ijth element of A. So, this is m cross n matrix. Then suppose you take m equal to 1, means you have just one row and then you have n columns, but in each column you have just one element. So, then you get a row vector, and for n equal to 1 you get a column vector. For m equal to n, A is called a square matrix, because if n is equal to n, then you have a square array of numbers. Then we define the transpose of a matrix as A transpose equal to. So, here you have rows a11, a12, so on a1n, but in A transpose the same elements are there in the column. So, the ijth element of A is actually the jith element of A transpose, and A transpose is actually n cross m matrix. Then different columns of A are, say A1 equal to A11, A21, so on AM1 transpose, then this is the nth column, and then you can write A in this form, A equal to A 1 the first column, A 2 the second column, so on, A n is the nth column. Similarly, you can write A as the combination of different rows also, means you take first row here, second row, third row, and so on. Non-singular matrix. For a square matrix A, if the determinant of A is not equal to 0, then matrix A is a non-singular matrix. Rank of a matrix, suppose matrix A is of rank R. It means the matrix A has at least one R cross R minor which is different from 0. And how you get this minor? You take an R cross R submatrix of the matrix A. Then the determinant of that submatrix is called the R cross R minor. So, if you get at least one R cross R submatrix of A having determinant different from 0, and every R plus 1 cross R plus 1 minor of A is 0, then we say that the matrix A is of rank R. Anyway, if determinant of A is not equal to 0, it means the square matrix has rank. Say, suppose this square matrix is of order n cross n, then rank of A is equal to n, because you get minor of order n cross n which is different from 0. Now, suppose A is any m cross n matrix of rank n, then rank of A transpose A. What is the order of A transpose A? The order of A transpose A is this A is of order m cross n. A transpose is of order n cross m. So, the order of A transpose A is n cross n, and if the rank of matrix A is n, and this n is actually less than or equal to m, then A transpose A is non-singular, since its rank is n. Then we define identity matrix. It is a diagonal matrix, means diagonal matrix means except the elements of its diagonal, all other elements are equal to 0, and in identity matrix all the diagonal elements are equal to 1 and remaining off diagonal elements are equal to 0. Then we define inverse of a matrix. For a square non-singular matrix A inverse is a matrix such that A inverse A equal to I n. In fact, A inverse is also I n. So, whether you pre-multiply A by A inverse or post-multiply A by A inverse, you get identity matrix of order n. Then idempotent matrix. Now, suppose A is a square matrix and the square of A means A multiplied by A is equal to A. Then we say that A is an idempotent matrix. Now, suppose A is m cross n matrix of rank n, and we define a matrix which is equal to I m minus A transpose A inverse A transpose. Then this matrix is an idempotent matrix. Now, this result can be easily verified. You have I m minus A transpose A inverse A transpose. You multiply it by I m minus A transpose A inverse A transpose. So, what you get? I m, then you have minus this into I m, and then you have I m into this matrix. So, you get 2 times A transpose A inverse A transpose, then plus A transpose A inverse A transpose, then you have this matrix A transpose A inverse A transpose. Now, this matrix is actually equal to, you have A transpose A inverse equal to identity matrix. So, finally, you obtain minus 2 times A transpose A inverse A transpose plus A transpose A inverse A transpose. Then you get, finally, you obtain I n minus A transpose A inverse A transpose, which is equal to this matrix. So, this matrix is an idempotent matrix, because square of this matrix is equal to the same matrix. Now, we define the quadratic form. Suppose A is a square matrix of order n cross n, and X is n cross 1 vector with elements x 1, x 2, x n. Then X transpose A x, you have X transpose means x 1, x n. In the middle you have matrix and then you multiply it by x. So, you have x 1 x n here, and then you simplify it. And finally, you obtain summation I equal to 1 to n, summation j equal to 1 to n, a I j x I x j. Now, this is called a quadratic form. At so many places we are going to use the quadratic form. Then we say that matrix A is positive definite if X transpose A x is greater than 0 for all non-null x. This is equal to 0 only when x is equal to 0. So, if this condition is satisfied, then we say that X is positive definite. Similarly, you may define the negative definite matrix also. If X transpose A x is less than 0 for all non-null x, then we say that A is negative definite matrix. Or we also define positive semi-definite matrix and positive negative semi-definite matrix. Now, at some places we will use the some of the matrix differentiation results. So, Of course, I am not going to give you detailed derivation, just I am giving you the results. Suppose you have a vector A and n cross 1 vector A, and x is also of order n cross 1. Then A transpose x is equal to summation j equal to 1 to n a j x j. Then we differentiate it with respect to vector x. Now, differentiation with respect to x means del over del x 1 del over del x n. So, this is equivalent to del over del x. Actually, you can easily prove this result. Suppose you differentiate it with respect to x 1, then what you get? A 1. So, you get the first element of A. If you differentiate it with respect to x 2, then you get A 2, the second element of A, and so on. If you differentiate with respect to x n, then you get A n here, the nth element of A. Then suppose you have this quadratic form x transpose A x, and you differentiate it with respect to x. Then you obtain A plus A transpose x, and if A is a symmetric matrix, symmetric matrix means A transpose is equal to A. Then we say that the matrix A is a symmetric matrix, means A I j, I jth element of A is equal to A j I for all I and j. Of course, we define this property of symmetric matrix just for square matrices. Then if A is a symmetric matrix, then del over del x, x transpose A x is equal to twice A x. So, this is how you can differentiate a quadratic form. Again, I repeat that I have not given the detailed proof of these results, and if you are interested in the detailed proof, then you must consult some good book, good matrix algebra book. My objective is just to introduce all these results related to matrix algebra, which we may require for future lectures. Then we consider linear regression model and the method of least squares. Now, suppose you have bivariate data on two variables x and y, and you have n pairs of observations. You have n pairs of observations x 1 y 1, x 2 y 2, so on x n y n. And suppose x is the input variable or independent variable, and y is the output variable or dependent variable. Your objective is to determine a relationship between dependent and independent variables describing the phenomena or the process in the best possible way. Means how the input variable generates the output variable. What is the process or what is the phenomena behind it? So, we want to describe that phenomena in a best possible way. Now, we come to the linear regression model, but before that I want to discuss in brief why this technique is called the regression technique. Actually, you have input variable x, and then you have a process. This is the process, and then you get the output variable y. And your interest is to investigate this process in the best possible way. And when you get data on x and y, you get the observations through this process. So, it is the process which is generating data, or your data has the characteristics of the process, or your data is capable of describing the characteristics of the process. Now, in fact, it is the data which has characteristics of the process, or it is the data which is generated by the process, and you do not know anything about the process. So, you want to assess the process on using the information contained in your data. So, actually you are moving in the reverse direction, means on the basis of the data you are trying to assess the process. So, that is why this technique is called the regression technique. Now, first we consider the simple linear regression model, which relates the input and output variables using a simple linear relationship y j equal to beta 1 plus beta 2 x j plus u j, j equal to 1 to so on up to n. You have n pairs of observations. Here beta 1 and beta 2 are unknown regression parameters, and your problem is to estimate these parameters. U j is the error term, and we assume that it has mean 0 and variance sigma square u. In fact, we also assume that all these u j's are identically independently distributed, means all the u j's are from the same distribution having mean 0, variance sigma square u. For any j not equal to j dash, u j and u j dash are independently distributed. So, such kind of set of random variables is called identically independently distributed random variables. And in fact, the interpretation of u j is like this: the difference between the expected and observed realizations of y. If you take expectation of y j, it is equal to beta 1 plus beta 2 x j, and this is the observed value of y j. So, if you take y j minus expectation of y j, then it gives you u j. Now, if you differentiate y j with respect to x j, then what you get? It is very simple, you get beta 2. So, actually beta 2 is the rate of change in expected value of y j with respect to x j, or expected change in y for a unit change in x j. So, this is beta 2. Then in linear regression, what we mean by linear regression? It is linear in regression parameters beta 1 and beta 2. It may be non-linear in x j, means your relationship may be of this type: y j equal to beta 1 plus beta 2, say log x j plus u j. This is also linear relationship, although this relationship is non-linear in x j, you have log x j here, but it is linear in beta 1 and beta 2. So, this is also a linear regression. Now, we come to the method of least squares to estimate beta 1 and beta 2, and this method actually we are going to use at different places, means at several places in our future lectures, particularly when we go for estimating the parameters of different time series processes like autoregressive process, etc., or when we fit the trend equation for the time series. So, in the method of least squares, we estimate beta 1 and beta 2 by minimizing the error sum of squares, which is equal to S equal to j equal to 1 to n y j minus beta 1 minus beta 2 x j whole square. So, suppose you have this bivariate data set, and then we have plotted that data set on x y plane. Such kind of graph is called the scatter plot or scatter diagram. And suppose this is your fitted line, then say you consider this point, say y j, this is your y j, and beta 1 plus beta 2 x j is actually this point, means this point is x j y j. So, you have x j here and y j here, and this point is beta 1 plus beta 2 x j, because this line is y equal to beta 1 plus beta 2 x. So, y j minus beta 1 minus beta 2 x j is this distance, means the distance between the point x j y j and this regression line parallel to y axis. We are not taking the perpendicular distance. Why we prefer this distance parallel to y axis? Actually, remember that when you are running regression between y and x, then your main focus is predicting the value of y on the basis of x. So, you will prefer to minimize the prediction error for y. And what is the prediction error? Say for jth point, this is the predicted value of y and this is the actual value of y. So, distance is this, the distance between this point and regression line parallel to the y axis. If you are interested in predicting the value of x on the basis of y, then you should choose the distance parallel to x axis. So, we minimize this error sum of squares with respect to beta 1 and beta 2. Now, for obtaining the least square estimators of beta 1 and beta 2, suppose beta 1 hat and beta 2 hat denote the least square estimators, then we differentiate s with respect to beta 1, and in fact, if you differentiate s with respect to beta 1, then you obtain minus twice summation y j minus beta 1 hat minus beta 2 hat x j equal to 0. Now, this gives you the first normal equation. These equations are actually called normal equations. You get this normal equation. Similarly, if you differentiate with respect to beta 2 and take beta 1, beta 2 equal to beta 1 hat, beta 2 hat and put it equal to 0, then you get the second normal equation. Now, you can easily solve these two normal equations, and the final expressions for beta 1 hat and beta 2 hat are beta 1 hat equal to y bar minus beta 2 hat x bar, which you get from here. Just divide both sides by n, and then you solve it for beta 1 hat. Y bar is the mean of y j's, x bar is the mean of x j's. Similarly, you can obtain beta 2 hat also. We write beta 1 hat equal to b 1, beta 2 hat equal to b 2. An alternative formula for b 2 is r s y upon s x, where s x square is the variance of x and s y square is the variance of y. R is the correlation coefficient between x and y. Then predicted value of y is y j hat equal to b 1 plus b 2 x j. Prediction error is E j equal to y j minus predicted value of y. Now, the total variation in y, you take y j, subtract the corresponding mean, take square of this and take summation over j. This is the total variation of y's. And then variation explained by the regression is you take y j hat minus y bar whole square, take summation over j. So, this is called the variation explained by the regression. So, this is the total variation, and this is the variation which has been explained by the regression. And when you say that your regression line is good, when most of the variation in y j is explained by the regression, means if you take ratio of these two, this quantity divided by this quantity, then this ratio should be large. Well, at the most this ratio can be 1. Now, if you take you can write summation j equal to 1 to n y j hat minus y bar whole square equal to y j hat is equal to b 2 y, actually y j hat minus y bar is equal to b 2 x j minus x bar. So, from here you obtain b 2 square summation j x j minus x bar whole square, then summation x j minus x bar whole square is equal to n times s x square, this quantity, this is n times s x square, and b 2 square is equal to r square s square y upon s x square. So, finally, you obtain this equal to r square summation j equal to 1 to n y j minus y bar square, because this s x square will cancel out, and you get n times s y square, and n times s y square is this quantity. Now, if you take ratio of these two, then ratio of these two is equal to r square. Now, this is another explanation of the correlation coefficient r square. R square is actually the amount of variation explained by the regression divided by the total variation present. This is the total variation present in y j's. So, if r square is large, means if r square close to 1 means the maximum, a large amount of variation has been explained by the regression. A large amount of variation in y j's has been explained by the regression. So, then we say that the regression is good. So, this quantity is a measure of goodness of the regression. Then multiple linear regression model and method of least squares. In simple linear regression, actually you have just two variables, one dependent and one independent variable. In multiple regression, you have more than one independent variables. For example, if you take the selling price of a house, then selling price of a house depends upon so many variables. It depends upon location of the house, it depends upon the carpet area of the house, whether house has sea facing or not, or it has some other beautiful facing or not, in some lake or some hill like that. The number of bedrooms the house has, the number of bathrooms the house has, how old the house is, etc. So many variables are going to affect the selling price of a house. Then what is causing variation in the dependent variable? In this question you may be interested. Say we have formed a list of such variables, but it may happen that some of these variables are not very relevant to selling price of the house. So, then which variables are causing variation in the dependent variable? Then which variables are mainly responsible for variation in the dependent variable? So, you may like to answer such kind of questions, and for that purpose you require multiple linear regression. So, again we take n observations on the dependent variable, then you have n observations on the jth independent variable, and in all you have k independent variables. So, these are the n observations on the jth independent variable, and j varies from 1 to k. Then we assume the following linear relationship between y's and x's. So, you have n observations on y, then y 1 is equal to x 1 beta 1 plus x 1 2 beta 2 plus so on plus x 1 k beta k plus u 1 and so on. So, you have this n set of equations. Now, we write this set of equations in matrix form using matrix notations. Anyway, here also beta 1, beta 2, beta k are the unknown regression coefficients, and if you differentiate expectation of y with respect to x j, then you get beta j. So, again you get the interpretation of beta j as the amount of change in expected value of the dependent variable y for the unit change in x. Then u 1, u 2, u n are IID random variables having mean 0 and variance sigma square u. Sometimes we also require the assumption that these errors follow normal distribution. Then expectation of u t is 0, variance is sigma square u. And again in multiple regression also you use the difference between actual value of dependent variable and the value predicted by the multiple regression. Just like the simple linear regression, here also you have the same interpretation. Now, we write the model using the matrix notations. So, y is n cross 1 vector of observations on the dependent variable y. X is this n cross k matrix of observations on each of k independent variables or each of k input variables. Beta is k by 1 vector of regression coefficients, and these regression coefficients are unknown. So, your problem is to estimate these regression coefficients, and again u is n cross 1 vector of errors. Sometimes we also call it disturbances. Now, in matrix notation, then you can write the model 1 as y equal to x beta plus u. U follows normal 0 sigma square u I n. So, if you are using matrix notations, then things become very compact. You have very compactly written the entire set of n equations. Then we assume that rank of x is k, and remember x is n cross k matrix. So, this assumption implies that x transpose x is non-singular. And suppose B is the least square estimator of beta. So, your problem is to obtain this B, and we obtain B by minimizing the residual sum of squares s equal to y minus x b transpose y minus x b. So, for obtaining B, we minimize S. Now, we can write S as, say, S is equal to y minus x b transpose y minus x b. So, this is equal to y transpose y minus b transpose x transpose y minus y transpose x b plus b transpose x b. Now, remember that what is the order of b transpose x transpose y? This is 1 cross k, then k cross n and n cross 1. So, this is 1 cross 1, this is also 1 cross 1. And you also notice that y transpose x b transpose is equal to b transpose x transpose y, and transpose of a scalar is the same scalar. So, these two are equal. So, we write it as y transpose y minus 2 b transpose x transpose y plus b transpose x b. Now, you have two options, either you differentiate it with respect to b, put it equal to 0, and then you try to solve it for b. This is one option which you can try. I am giving you an alternative derivation. Say, we write it as b transpose x b minus 2 times b transpose, and then we write here x transpose x, again we have x transpose x inverse to compensate for this x transpose x. Then you have x transpose y here, plus we have added y transpose x, x transpose x inverse x transpose y, plus you have y transpose y, and since you have added this quantity, you subtract this quantity. Now, you combine these three terms. So, you can write these three terms as b minus x transpose x inverse x transpose y transpose. In the middle you have x transpose x, then b minus x transpose x inverse x transpose y. So, for example, the first term is b transpose x b, which you get from here, and then the second term minus 2 times b transpose x transpose x inverse x transpose y, which you can obtain. Say, you have b transpose x transpose x inverse x transpose y, etc. And then v is equal to this quantity, and you write it equal to y transpose and y, where m is equal to this. Now, notice that this matrix x transpose x is a square non-singular matrix, and this is also a positive definite matrix. In fact, suppose you write this entire quantity equal to C, then you have C transpose x C, and then you write x C equal to D. So, you get D transpose T. d is equal to x c, or you get summation d j square. Now, this is greater than 0, and when this becomes 0, means if this quantity is greater than or equal to 0, then the minimum possible value is 0, and that minimum occurs when B is equal to x transpose x inverse x transpose y. So, this is the value of B which minimizes S. Oh, we have shown this result here also for any p cross 1 vector C, C transpose x C is greater than or equal to 0, and it is 0 only when C is equal to 0. And then minimum value of this force is 0, and this value is attained when B is equal to x transpose x inverse x transpose y. So, this B is called the least squares estimator of beta, and the error sum of square is V equal to y transpose m y. In fact, B satisfies many optimal properties. It is the best linear unbiased estimator. It means it has the minimum variance in the class of all linear unbiased estimators of beta. Then an unbiased estimator of sigma square u is V upon n minus k, and if u follows normal distribution and then you try to find out the maximum likelihood estimator of beta and sigma square u, then MLE of beta is again B, and MLE of sigma square is sigma head square u equal to V upon n. Now, we write the model in deviation form. So, this is the OLS regression y equal to x b plus e is the OLS residual, we call it least square residual. Now, suppose you define any matrix A equal to I n minus 1 upon n ln transpose. Ln is n cross 1 vector with all elements equal to 1. Then for any vector y, 1 upon n ln transpose y. What is ln transpose y? Ln has all elements equal to 1, and then you have y. So, ln transpose y is equal to summation y j, and 1 upon n ln transpose y is y bar. And if you take a y, you multiply a by y. So, you get y here minus 1 by n ln transpose y is y bar. So, you get y bar ln. Ln has all elements equal to 1. So, each element of a y is means the first element is y 1 minus y bar, second is y 2 minus y bar. So, pre-multiplying any vector by a leads to a vector with observations as deviation from their means. Now, we consider the analysis of variance for multiple regression. Then you can easily verify that A is a symmetric idempotent matrix, and if you post multiply A by ln, then you can easily verify that A ln is equal to 0. Then in regression, you know that these least square residuals are uncorrelated with the independent variables, and so x transpose E is equal to 0. You can verify it also, and A E is equal to E, because E has in the errors have mean 0. So, deviation from mean means the same errors. A is a symmetric idempotent matrix, and first column of x is corresponding to the intercept term. So, it has all elements equal to 1. So, we partition matrix X in this first column and remaining k minus 1 columns. So, X 2 is n cross k minus 1 matrix, and then you can write y equal to ln b 1 plus x 2 b 2 plus e, where actually we have partitioned B also. This is the first element of B, and these are the remaining k minus 1 elements of B. The first element is corresponding to the intercept term, and remaining B elements in B 2 are the slope coefficients. Just like the linear regression, when you have beta 1 as the intercept term and beta 2 as the slope coefficient. Now, suppose you take y transpose A y, then what is y transpose A y? This is summation y j minus y bar square. Actually, A y gives you the deviation from mean. Means you have a vector with elements y 1 minus y bar, y 2 minus y bar, so on, and y transpose A y is equal to A y, because A is an asymmetric idempotent matrix. So, it is equal to A y transpose A y, and you can easily verify that this is y j summation y j minus y bar square. So, this is your total sum of squares, and it has n minus 1 degrees of freedoms. Actually, j varies from 1 to n. So, you have n elements in this sum of square, but there is one restriction, summation y j minus y bar equal to 0. So, the degree of freedom is n minus 1, and then this quantity B 2 transpose x 2 transpose A x 2 B 2, this is called the explained sum of square, and it has k minus 1 degrees of freedoms. Again, I am not going into the details, but this is the total variation in y's. This is the amount of variation explained by the regression, and then you have residual sum of square, which is E transpose E. E transpose E has n minus k degrees of freedoms. Total sum of square in y j's, then you have explained sum of square, the part of variation in y's which is explained by the regression, and then residual sum of square. So, unexplained part, the part of variation in y's which is unexplained by the regression. And for a good regression, this should be small, error sum of square should, or residual sum of square should be small, and this part should be large. One more thing you notice that the sum of squares are additive. Total sum of square is equal to sum of square explained by the regression, explained sum of square plus residual sum of square. Actually, corresponding degrees of freedoms are also additive. N minus 1 is equal to k minus 1, the degree of freedom of this part, plus degree of freedom of residual sum of square. So, degrees of freedoms are also additive. So, this is the ANOVA table for the multiple linear regression model. You have sum of squares here, degrees of freedoms here. Then we obtain the mean sum of square. We divide the total sum of square by corresponding degree of freedom. So, we get mean sum of square, mean sum of square. This is mean sum of square explained by the model. This is mean residual sum of square, and then you can obtain the F ratio also, just like the usual analysis of variance table. Now, to check how good your regression model is, You may take error sum of squares as one of the measure. In linear regression, a measure of goodness is r square. Here we have capital R square, which is equal to explained sum of square divided by total sum of square. And so, this is a measure of goodness of fit of the model. This gives you the amount or fraction of variation explained by the regression and the total variation in Y's. And whenever we add any variable, r square always increases. So, another measure is adjusted r square. Now, apart from these measures, we also have some other model selection criterion. Two criterion are Akaike information criterion and Bayesian information criterion. If k is the number of estimated parameters in the model, theta hat is the estimated k dimensional parameter vector and L theta hat is the estimated likelihood function, then we define AIC like this minus 2 times log L theta hat minus k. And how can you use AIC? If there are G candidate models and you have to select one of those models, then you fit all the G models, calculate AIC for each of these models and then select that model which has minimum AIC. Then another model selection criterion is Bayesian information criterion, which is popularly known as BIC or Shewhart's information criterion. Again, BIC is defined as minus 2 times log L theta hat plus k log n. So, these two information criterion AIC and BIC. These criterion have two components. One depends upon the likelihood or minus of likelihood. As whenever you add any variable, the first part always decreases, but the second part, say for example, in BIC k times log n increases. So, it gives penalty also to complexity of the model. So, one can use any of these criterion as model selection criterion. So, today in this lecture I have covered some of the main results of matrix algebra as well as the simple and multiple linear regression models. We have discussed the method of least squares, some model selection criterion, and then we also discussed the analysis of variance table for the multiple linear regression model. Although these topics are not directly connected with the time series, but we use all these techniques in the time series. So, now I am going to stop here. Thank you.